Hey, welcome back. This lecture is going to be on sets and unordered lists. Basically, with the set part, we're just going to be quickly talking about some of the ADT you might involve dealing with sets and some of the variances and things you might run into. And then unordered lists will take up the lion's share of the lecture, dealing with exactly how we can handle a structure when we have no ability to order anything that we've done or any of the items we have. So, when dealing with the set ADT, as before, we've got a number of assorted operations we might have. The important idea about a set ADT, though, is that you're representing sets rather than linear collections. And so, though in the past we've had the linear collections of elements, you had one successor and you had one predecessor, and then we dealt with trees where you had one predecessor, a parent, but your children were your successors, and there was a number of those. With a set, there's no ordering to any of the elements. You just have some random collection of values. So you have here 1, 2, 5, 7, 3, and they're just in some collection without some sort of order. Now, if you traverse the set, you're probably keeping track of these values using some data structure behind the scenes, and so they might well be in some order behind the scenes that would determine how you traverse it. But conceptually, there's no order. We're just saying, okay, give me any random value for my first value, and then print out the next value in the set, and then the next one, and the next one, and the next one. And the kind of things we'd be using for sets would often be situations where we'd say, if I get the values in the order 2, 5, 1, 3, 7, that's the same as if I have them in the order 7, 2, 5, 1, 3. The point is we have a collection, not so much what order they're in. Now, we may extract them in some order. So you may say, well, as we'll see priority queues later on, we'll say, well, we might want to extract them in a particular order, the minimum, and then the next minimum, and then the next minimum. Or if they happen to be stored behind the scenes in order and you say print them out, they always come out in order. But the idea would be that conceptually that wouldn't really be a big deal. The important thing would be that we have a collection and conceptually it's just a collection that aside from some specific rules on a specific application for pulling things out in a certain manner, we would just say give us the set of values, print them out, and any ordering we get would be acceptable. So that's the difference between sets and things like trees and lists. We don't really have any sort of preset ordering for this. So you might want to insert an element into a set. You might want to remove a particular element from a set. You might be concerned if a particular element is a member of the set. So you're almost doing a find here and saying, return 1 or 0. In addition, and if you had some sort of a discrete math course, you may have, learned about set union or set intersection, where you're saying, create the collection of the set containing all elements that are in A or B, and then find the set containing the elements that are in A and B, and a few other set operations like that. So the typical things you might do on a set, a union intersection, there's set difference we might talk about. Those are the kind of things we're generally concerned with. So we can put difference here as well. Just your general kind of the same operations you'd run on sets in discrete math proofs or whatever, or operations. Those would be the kind of things we're concerned with here. Now, typically, or I shouldn't say typically, but the most general version of sets does not require any sort of specific ordering. The elements you're holding may not have the ability to be sorted in any way. Now, in real-life applications, most things we get can be sorted in some fashion if you want to make use of some sort of a key. So even if you're storing submarines, you can say, well, every submarine has a name, and so we can sort them by name or something like that. You have student records, and those student records, even though they're just these behemoth objects, could be sorted by social security number or by the student last name or by the student first name or their hometown or whatever. And so there's usually, in some sort of complex record, a number of different integer-based or character-based keys that we could do some sorting on. But the general conception of an element is that, if you have a particular type, there's no inherent need for that type to be something that you can sort. There's no inherent concept of an ordering, though realistically we usually can find some way to do it. But the most general idea then would be that we can't necessarily order these elements. If we can, then we can add an extra element an extra method to that ADT. I mean, these are not the only methods we could have by any means, but one thing we could definitely add to the ADT would be a min element, or min method, which would return the minimum of the set, and that might be very important to us. But the idea then would be we obviously can't return the minimum unless there's a concept of a minimum in the first place. Though again, what you may have learned in a discrete mathematics course is that the sort of sounds like common sense, but it's called the well-ordering principle. If you've got some order, some ability to take any two elements and determine which one is less than the other, then there's definitely some minimum element. You know, you can't have three elements and have A is less than B, and B is less than C, and C is less than A. That doesn't make any sense. So if you can order the elements, there will be some minimum that you could return. Now, one of the important things for us, and we've sort of alluded to this already in the previous lectures on trees and lists and stuff, but we'll sort of formally discuss it now, is the idea that often we have not just a key that we're worried about, but we have here a pair with some key and some info. And I was even just saying that, you know, just a little while ago, where we say if we have a record that we want to sort on some keys. So we say, okay, we've got a student record, and the idea of a student record being less than some other student record doesn't make sense. But we could sort them by social security number and say one social security number is less than the other one. Now what we've got then is we're saying the info is the entire student record. I was going to abbreviate it, but I won't. Here's your student record, and here's the social security number of the students. And so you can have a pair like that and that would be the kind of thing we mentioned even back in the B-tree lectures, where I said, okay, you can say the whole B-tree stores social security numbers, for example, but when you hit a leaf node and you're checking a social security number, then you've got also a pointer to a student record along with that. And then the social security number would be part of that student record. Likewise, you can have situations like that where the info does not contain the key. Here your record would contain the key. The key would be a particular piece of the record. And so here's what you look up on, and then you've got a pointer to the entire record attached to that. What you could also have would be something like, well, consider using a phone book, where you look up a name and you get a phone number. In that case, the name and the phone number have nothing to do with each other. I mean, they're related, but I'm saying it's not like the name is some component of the phone number in the same way that a social security number is a component of a student record. So in that case, there's two completely different sets of data, the names and the phone numbers, but there happens to be a relation we're establishing here, where this particular name is tied into that particular phone number, and so we store those two as a key info pair. And a lot of times, that's really how things work out for the kind of things we've been doing so far, and the kind of examples we've been using, the kind of examples we've had so far, and the kind of examples we'll continue to have. We're usually just searching for a string or an integer, and that's all we have. But in reality, often what these things are, I mean, sometimes they're legitimate data, and sometimes they are keys to some other records, and we're searching those. And so often you'll have this kind of a setup. And don't be distracted by the fact that, oh, we're only showing, you know, this particular data structure. We're just looking for numbers or not looking for numbers. Generally, what's going on is that you could just as easily have taken anything we've looked at so far or anything we'll look at in the future and expand it from just storing a key to storing a key info pair and having the code search on that key, but return the entire information record. And there's you know, that's a trivial change to make to any of the stuff we've looked at. So we do end up then with the idea of a function called lookup, where lookup takes some key and returns the info. Up to this point, we've mainly discussed find, which would be, you know, you take some key and you return whether it's there or not. The idea of lookup would be take some key. If you find it, there'll be an information record attached to that key, and that's what you want to send back. So you're not really concerned when you do in the university database, if we do a lookup on your social security number, we're not concerned with saying, hey, is this social security number in the database or not? You know, what we care about is give us a student who has this social security number, and that's a little bit different than a find. So a find, or as I wrote in the previous slide, is member, is sort of conceptually the idea of is this element in the set or not. With a lookup, we're saying if the key is in the set, then return the information record associated with it. And if the key is not in the set, you can return null or however you happen to code things. But that would be the idea of a lookup. Which is, and we've mentioned lookup in the context of arrays, and in a sense that's what an array allows. We look up by an array index and get the value in the cell at that index. So in a sense, we're dealing with this key info pair by writing an array, where the array says you have a mapping between the array index and the item stored there. And so conceptually, an array does this, even though implementation-wise it's a lot faster than searching for the pair 1 comma element and 2 comma element and so on. We can just jump right to that index. So then by way of a final definition, you often see the concept of a dictionary ADT. And what that is an ADT where we're mainly concerned with supporting insert of a value, remove of a value, and lookup. Where here, when we say insert X, what we're really saying is, what we're really doing here is we're inserting a key info pair. When we say remove, we say I want to remove a key, and I would remove the info with that. And when we say lookup, I'm saying I look up on a key and return the info just like I did up here. And so, we can support a bunch of other stuff, but generally when we talk about a dictionary, that's what we're talking about, is we're mainly concerned with just supporting those 3 operations, and that's the main concern. And so, plus constructors and whatever else. So then the idea is anything we've looked at so far can pretty well be a dictionary ADT. You can insert and remove and do lookups on a linked list, or on an array, or on AVL tree, or a binary tree, or a B tree. And so all the sort of things we've looked at could be implementations of dictionary. And of course, you can think of in the real world of a dictionary. You look up a word in English and you get the definition. That's exactly this kind of idea. The word is the key, the definition is the info. But this is a more general concept, not just meaning verbal dictionaries, but in general, this idea of saying I want to insert and remove these pairs and simply look up on a key to get the info. And if you can do that, then you've got a dictionary. And those dictionary operations, those 3, insert, remove, and lookup, tend to be primarily what we're concerned with when discussing a lot of different data structures. Not always, sometimes other things as well. But generally, those are the 3 we tend to try and implement first, because a data structure isn't really of tremendous use unless you can actually insert and remove items from it, with some exceptions. And once items are there, you want to be able to retrieve them. And so if the data structure is meant to hold information, you want to be able to alter the particular pieces of information that are in your structure and be able to find them later on when you need them. So that's why those are sort of very fundamental. So, that said, let's consider the problem of having a particular collection of elements that do not have an ordering, because the simplest version of a set, or the most general version, would not allow that. Your E-type is no less than operator, whatever your E-type happens to be. And so we can't use AVL trees or binary search trees. We can't use B trees. We're sort of stuck with these structures that didn't require an ordering. And an array, we could have an unsorted array if we wanted. We could have an unsorted linked list, and we could have a general tree, an ordered tree, but that wasn't a search tree. So those are sort of the 3 things we've looked at so far that would allow that kind of structure to be in place. Everything from binary search trees on, which was binary search trees, AVL trees, and B trees, required that you could have an ordering on these elements in order to work. So now when you think about what kind of things might be helpful, well, we had the, some operations for the set ADT on the previous slide. When we talk about union and intersection and inserting and removing, and generally, of course, we might want to traverse the entire set too and print everything out. And certainly, if we're just trying to concern ourselves with just grabbing elements easily to do searches for unions or whatever, the ordered tree in that case isn't really going to give us anything of great power. If there's a particular reason the ordered tree, the structure of it would help, like I believe I mentioned at the time, if you're representing a corporate hierarchy and you have the president and the children are vice presidents or whatever, then that's a different story. But if you just have a glob of elements, a collection, a set that you're trying to represent, there's not really anything that the tree structure is going to give you that you don't already have with a linked list or an array. Because you can traverse, but it requires recursive calls to do easily. With a linked list or the array can be traversed pretty easily, even without recursive calls, which can make them a little bit more efficient. You've got extra memory when you're using a tree as opposed to an array or a linked list. And inserting can be a little bit more of a pain because you've got your question as well now, where do you insert and what do you do with the children and so on. And so you're not really going to gain anything from using a tree, in most cases, that the linked list wouldn't have given you for the particular issues we're worried about, namely just taking collections and getting a union of them and so on and so forth. Or searching for is member. It takes order and time, as we talked about with the traversals, even to search a general tree. We can't get the logarithmic time at all until we make it a search tree. So if we don't need the particular structural advantages a tree gives us, then we may as well just go ahead and use a linked list or an array. And some of the things we'll be talking about will involve being able to manipulate nodes and move nodes into different places in the collection. And as we've seen, that's a lot easier to do with a list than with an array, because every time you want to pull a value out of the array, you need to do shifting to take that spot over. And every time you want to insert something, say, in the middle of the array, you need to shift everything over to make space. So this is where we get the idea of an unordered list. An argument can be made that if we just simply have a collection of elements that don't have an order, and there's nothing else we know about them. There's no particular index value that makes looking up easy, or we don't need a tree structure. Then a list provides us with a nice flexibility because it provides linear search times just like the other two, and yet we can manipulate the various nodes in the middle easier to move them to different places, like we're going to see what we want to do in a moment. And so for what we're about to do, the list is going to be a nicer structure than the array or the tree, and so the unordered list is going to be what we look at. Unordered meaning it's not sorted. Now, to make life easy and have the example easy, I'm going to use strings, and you can say, well, wait a minute, you could put a less than in a string class. Yes, you can. So let's just assume for the moment, we either don't have a less than operator for strings, or, in other words, just accept that we don't have that yet. Even though we could technically put it in, I want to use an example of things that are clear to understand, so I don't want to go messing with some behemoth objects that aren't obvious how to sort them. So I'm going to use strings, but for the moment we'll say, for the whole lecture today, we're going to say, assume we don't have the ability to sort strings, simply because they'll make a nicer example than a bunch of objects that might not have a less than defined. So we'll say we left a less than out of our string. We can't put things in alphabetical order, and we'll use that as the example, even though technically they could be an orderable type. So don't get too messed up with that. And what we're going to do here is say, let's say we have the names Bob and Sue and Fred and Jim and Betty. Those will be 5 names that we have. And we can put them in a list. So let's go ahead and write them in a list. We'll have here head, Bob, Sue, Fred, Jim, and Betty. And hopefully, even if those names are not entirely legible from those nodes, it's at least clear what name I meant. Like Betty is probably not too legible, but it's Betty, because the others obviously are not. So now the idea will be we're going to assume we can't sort these values. We haven't put actually, one thing I might mention is even if conceptually you can sort them, we can say, hey, you could have put a less than operator in the string class, and then you can compare these against each other and sort them. You might have had a situation where the string class you happen to be using, you're using precompiled library code that doesn't provide a less than. So maybe university folks write their database and they're using precompiled that they bought from someone else for a library, a precompiled student record class that didn't provide the ability to order the nodes based on anything. So even if conceptually you could add a less than, you may not have had that less than put into your code in any way, and therefore you couldn't use it. But again, the idea is, I don't want to draw monolithic objects here, so I'm just going to go ahead and use strings, and except for the sake of the lecture, we'll assume we have no means to order our strings. They're just elements that we need to store and search over. Because that's going to be our concern here. If we have a set of elements that we can't sort and therefore can't use an AVL tree or anything else like that, how can we deal with trying to optimize the collection? And the issue here is, well, what do we mean by optimizing the collection? We mean there are a number of ways this list could be arranged. I have 5 elements here, so there's 5 factorial ways this list could be arranged, which is 120 different ways. The more elements you have in this list, the more different ways it can be arranged. And the question is, well, what order is the best? Or is there no answer to that? And I could say, well, we're going to assume for the moment that all these values are equally likely to be looked up. That is, okay, Bob is looked up 1/5 of the time, and Sue is looked up 1/5 of the time, and likewise for Fred and Betty and Jim. So we'll do a number of lookups. We have a collection of these 5 elements, and in general it would be a collection of many, many more elements of some type we couldn't order. But we're saying we've got now a collection of these elements, and now our concern is, well, we're going to do many lookups. We're going to do many, many lookups on this collection of people, and what I want to do is say they're all equally likely to be looked up. What's the best order for the list? And you may, of course, through common sense know already what the answer to that question is. But what we can do is explore this. I'm only going to go over this quickly simply because some people don't always know it. But there's the idea of expected value. I'm not going to really spend much time on this at all. So if it's a review for some people, don't worry too much. Expected value, when we say the expected value of something, of some event, we can say that what it's going to be equal to, and this is just, I'll write the mathematical notation, and then we say the cost of I times the probability of I. So that's our expected value. I'll explain what that means now, but that's in terms of notation. We say over all possible I, the cost of I times the probability of I. And we say, what on earth does that mean? Well, imagine a lottery ticket. You have 2 possible outcomes. You could win $1 million, or you could not win anything. And so you say, what's the cost, or what's the cost or the value of a ticket, where you say, you have your $1 million, and maybe you have a 1 in a million chance of winning, or you say 1 in a billion chance of winning. So let's say those are your odds in this particular lottery of winning. Plus, and you say, well, what's the cost of the other alternative? Well, you may also win $0, and the chance of that happening is pretty much 999,999,999 over 1 million, because you either lose or you win. So if that's the chance you lose, this is the chance you win. And so given that, well, we say, what's the expected value? In this case, of course, in this case, you win nothing. And in this case, what you have is $1 million divided by, or times a billion. What you have here is the expected value of your ticket in that case is going to be $0.001. 1/1000th of a dollar plus nothing is 1/1000th of a dollar. So that's the expected value of your lottery ticket when you buy it. And so as a result, if the state charges more than that, I probably screwed up the math there. Anyway, the point being that if the state charges more than that, then they're making money, because each lottery ticket is valued at that much or whatever. And so, typically, the lottery ticket's valued at 54 cents, given, the particular odds of winning and the particular value of the lottery. And so they charge you $1 for it, and they're making money. So how does this factor in for us? Well, it's relevant for us because, and so now that's just sort of a quick and dirty example. I'll do the same thing on our list here, where we have here Bob, Sue, and Fred, and Jim, and Betty. And so we say, well, here's where we start talking about search times for ourselves, which is the only reason I even go over this to be in this topic in this class. What's the search time to reach Bob? Well, we do one node, one comparison. So the cost of finding Bob is one comparison, and we'll have to look at Bob 1/5 of the time. The cost of finding Sue is 2 comparisons. In other words, it takes a little longer to find Sue than to find Bob, times 1/5. The cost of finding Fred is going to be 3 comparisons, because we'll have unsuccessful, unsuccessful, and then we'll find Fred, likewise times 1/5. The cost of finding Jim will be 4 comparisons times 1/5. The cost of finding Betty is 5 comparisons times 1/5. Because each of them, there's the probability that we reach that node, and that's how expensive it'll be to get to that node. And of course, it's cost of 5 to get to Betty because you need 5 comparisons before we reach Betty. So that whole total there, 1 times 1/5 plus 2 times 1/5 plus 3 times 1/5, and so on and so forth, is just going to be 3. Turns out to be 15/5 divided 15/5, and that's 3, which is what we'd expect. So we've already, now this ties into the average case search time on a list, where we said we expect to have to search about half the list. That's what we do here. When we say you might look for any value, and it's equally likely you'd look for any value, we expect to search the middle of the list. And we had said that before. The average case was n over 2. And so how is this relevant to us? Well, this is relevant in that when we said, what's the ideal order for the list if all of these are equally likely? And the answer is there is no ideal order. Any list is okay. Rearrange this list and have the 5 names in any order you like, and you'll still have this same workout. If you're equally likely to look up any value, then you don't really care what order the values are in. The math will work the same way. The first node, whoever it is going to be looked up 1/5 of the time. The second node, whoever it is looked up 1/5 of the time. The third node, whoever it is looked up 1/5 of the time, and takes 3 comparisons to reach, and so on. However, what if we happen to know in advance? Say we knew. Here we have the names again, where we have Bob, Sue, Fred, Jim, and Betty. And I'll draw this list twice. So here we have, this is the list we've been looking at so far, which sort of crammed on the other slide, so I want to redraw it. Bob, Sue, Fred, I'll just abbreviate the name so I have more room. Jim, Betty. And let's say it turns out, okay, Sue's pretty important and gets looked up 30% of the time. And Jim gets looked up 20% of the time, and Bob 20% of the time, and Betty 15% of the time, and Fred 10% of the time. And that adds up to 100. So, over the course of our lookups, those are the proportions we expect. Instead of saying everyone's looked up 20% of the time, in other words, they're not all equally likely anymore, now Sue is more likely to be looked up than Fred or Jim or than anyone else. So now, if we were to run that, we can say, well, now we might have an optimal arrangement, because we can say, well, Bob's got a 20% chance of being looked up, and its cost is 1, plus Sue's got a 30% chance of being looked up times the cost of 2, plus Fred's got only a 10% chance of being looked up times the cost of 3, plus, we look up Jim 25% of the time times the cost of 4, plus, and we look up Betty 15% of the time times the cost of 5. And that turned out to be 0.20 plus 0.60 plus 0.30 plus 1.00 plus 0.75. And if you add that up, you have 80, 1.1, 2.1, 2.85. That's the expected number of lookups now. If we add up all the cost of all our lookups over a long time, then divide by all the lookups we did, we expect that kind of an average. That we'll do about 2.85 comparisons. Similar to how they say, okay, certain families have 1 kid, and certain families have 2 kids, and certain families have 5 kids. And if you add up all the kids and divide by the total number of families, you end up with 3.2 kids. No one actually ever has 3.2 kids. That would be a little odd. But that's the average number of kids. And this is the average number of comparisons per lookup over a number of lookups. That's what we expect, provided I've done the right math and not screwed something up here. So we say, well, is this the optimal arrangement? Because I can certainly see now switching around Sue and Bob would improve things. Because if I was to move Sue as the first node, that would be 0.3 times 1 and not 0.3 times 2. So I'd get just 0.3 times 1 plus 0.2 times 2 if I was to just switch Sue and Bob around. I'd have that calculation. Right now, together, they add up to 0.8. But if I switch Sue and Bob around, I'll get 0.3, which is Sue's lookup percentage, times 1. Bob's lookup percentage is 20%, 0.2, times 2, and that adds up to 0.7 instead of the 0.8 here, which means right away we'd be doing better. And in fact, hopefully it's a somewhat common sense too, the concept of if we arrange them by these probabilities, then that will be the optimal list. Once we actually have unique probabilities for each person, that we look up each person a certain amount of time, then arranging them in that form would be the best. And I would expect that's probably, somewhat intuitive as well, but I at least wanted to kind of explain, go over a bit of math and say, well, it's not just an intuitive issue, it's fact as well. But if we have Sue here, and then Bob, Sue here, and then Jim, and then 0.20 is Bob, and then Betty, and then Fred. Sue, Jim, Bob, Betty, Fred. Well, then we can simply quickly run the math. 0.3 times 1 plus 0.25 times 2 plus 0.2 times 3 plus 0.15 times 4 plus 1 times 5. You're not going to have to do this on the exam. I'm just using this as an illustration. And so you get 0.3 plus 0.5 plus 0.6 plus 0.6 plus 0.5. And that adds up to 1, 2.2, 2.5. In other words, we're saying this is the best we can do. And the reason it's the best we can do is not just we run the math or the math there just to establish that we do know what we're talking about. But the idea here is by putting the person that's looked up most frequently in the front, then you say, well, that makes sense, because if this person's going to be looked up most frequently, that's going to be the node we look at. If Sue is further on down the list, in terms of arranging this as a data structure, if Sue is further down the list, then the problem we will run into is that we won't have the ability to, we will be doing more comparisons to reach our most frequent element. We want to reduce the number of comparisons involved to do the most frequent element. And likewise, Fred we never look up, only 10% of the time. So it's okay for Fred to take a lot of comparisons to find because we don't look up Fred that often anyway. And so that's the idea here. If we arrange them in order of probabilities, 30%, 25%, 20%, and so on, in the order of decreasing probabilities, then we're better off. And then I've got the math. We got the math here to kind of verify to yourself that yes, we do have expect a fewer number of comparisons if we arrange the list that way than if we arrange the list in some other random fashion. So as soon as we have differing lookup probabilities for these individuals, then it's a different story. Then there is some optimal order to the list, and the optimal order to the list is in order from maximum to minimum lookup probability. And hopefully, like I said, hopefully that's somewhat intuitive as well. So you're asking, well, why do we care? And the answer is, there's kind of a flaw with this argument, because otherwise we say, hey, great, let's go ahead and put everyone in order by probability. And then we got our optimal list. The problem is that we generally don't know those probabilities in advance. At the end of it all, I could say, well, I've been doing a bunch of lookups. Bob and Sue and Jim and Fred and Betty are in various clubs, and I have to look up their records so I can get their phone number and contact them about various university goings-on or whatever. And I say, well, the situation that I'm in then is at the end of the semester, I kind of note to myself, oh, wow, Sue was pretty important. I looked Sue's name up 30% of the time. And Jim was pretty important too, because I looked him up 20% of the time, 25% of the time. Not quite as important as Sue, but more important than the others. But at the start of the semester, I might not know how frequently I'm going to need to contact these people. It just turns out at the end I note, oh, wow, I really had to contact Sue quite a bit, and Jim as well, where Fred wasn't too important, and I only had to call Fred a few times. In a lot of realistic situations, we wouldn't know these probabilities in advance. And so ordering the list based on the probabilities is all fine and good, except if we don't know the probabilities, then we're stuck. And so what we turn to then is a means by which we can perhaps get at this ordering as best we can. We can't know it for sure because we don't know the probabilities for sure to the very end of the semester, but we can at least try and approximate it. And this leads to what is known as a heuristic. And a heuristic is a technique which we can't exactly predict the performance of, but which we expect works well in practice. In other words, a heuristic is a good rule of thumb. And we say if we do this, we don't expect it's going to be the best or that we can exactly predict what will happen, but we say, you know, this particular technique is we expect is going to be a good idea. We can analyze it a little bit and say, yeah, this will usually give us decent results. Or with an AVL tree, when you insert into an AVL tree, you know exactly what's going to happen and why and how it affects things. Here, since we're not quite sure how things are going to turn out in the end, we don't know if what we're doing is the best idea, but we expect that in practice it works pretty well. And that definition is in the textbook as well, so I'm not going to leave it up there any longer than that. But the idea here is, one thing we might do, let's say we go ahead and start with those percentages. So we have, again, we have Bob at 0.20, or actually, let me forget this. We have, one thing we can do is, if we have this as a list, and I'm just going to give the first two letters of each name because I normally can have this list on the whiteboard in class, but unfortunately I'm constrained on this paper, so I need to save some room. Make sure Betty's, you know, distinguishable from Bob. So if those are the names, one thing we can do is known as the move to front heuristic. The point of all this being that we can't really optimize the ordering of a list when there's no sorting involved because there's no ordering, and on top of it we don't have any means to you know, optimizing it's all fine and good, but we don't have any means of knowing what the probabilities will be anyway. So it's pretty much just a stab in the dark as far as you know, what would be the optimal order for this list. And so instead of taking a random guess, you know, Bob, Sue, Fred, Jim, Betty, and sticking with it, let's revise the ordering of the list with every lookup we do. Let's say, okay, we'll start out with this list, but with every new piece of information we get, we'll revise the ordering. And so one thing we can do is move the recently looked up node to the front. That is, let's say I do a lookup on Jim, what I will get then as a result of the move to front heuristic on that initial list is we'll have, I can just do it this way actually. Of course, it helps to actually put Jim in front. Jim, Bob, Sue, Fred, and Betty. So we're saying here we take Jim out from between Fred and Betty and put Jim in the front because that's the most recently looked up element. The other thing we can do, that's going to have some advantages. Namely, if it so happens that our initial value, our initial list, puts Jim way down in the end of the list, when Jim is really going to turn out at the end of things to have been a very frequently looked up element, then Jim will move to the front right away. And Jim will never filter down the list too much because if Jim is very frequently looked up, Jim would only drop a few cells down in the list before we pull Jim to the front again. Of course, we won't normally have a list of size 5. Let's say the list is size 500. Well, you know, Jim might float down 10, 15 cells into the list and then get pulled to the front again. So it only takes, you know, 15 lookups that time to find Jim, and then Jim's put in the front again. And that may frequently happen, where Jim keeps getting pulled to the front very often. Jim never gets to be filtered down to cell 499, where it would be really expensive to look Jim up, because we keep pulling Jim forward into the front. And so Jim, the elements that are looked up most frequently will tend to stay near the front of the list, which is a good thing for us. The other possibility is known as the transpose heuristic, which says move the recently looked up element up or forward one cell. And so we have here the idea of, say, head. If I look up Jim in this case, I still have Bob in the front, and then Sue is second, and then Jim moves up in front of Fred, and then we have Betty at the end. So in this case, Jim only moved up one cell. But we said every time we do a lookup for transpose heuristic, whenever we look up a value, we then say, well, I've just looked this up. That means, you know, it's something worth moving a node ahead. And say, well, inch it a little bit closer to the front, because if I've just looked it up, maybe it's got some relevance to me. And over time, the nodes that are looked up more frequently will make more leaps towards the front and will end up near the front of the list. Where items that aren't looked up too frequently might occasionally jump up one forward, but then will fall back a bit. And so the difference is basically one of, this is a very drastic change, this is a very non-drastic change. But there's advantages to the other one as well, so we can consider those. If we talk about move to front, what we can say is, well, move to front, the advantage of move to front is makes big changes quickly. So if your list is way out of whack, that means we can get close, not dose. I put the C and the L too close together. We can get close to optimal quickly. If our list starts out very far from optimal, well, by doing move to front, after we've done a certain number of lookups, we've managed to pull any values that should have been in the front that are near the end, we've pulled to the front pretty quickly. So the move to front isn't going to waste time. Anything, right away, the elements that are near the bottom of the list that we would have preferred to be in the front, they'll be in the front right away, because we'll do frequent lookups on them, and so they'll get to the front right away and tend to stay there. Or the transpose adjusts more slowly. So if the initial list is very wrong or very different than the optimal list, the transpose is going to slowly adjust the list to approach the optimal list, but won't quite get there very quickly. On the other hand, can't get too refined due to more drastic changes. So the idea will be, well, if you happen to look up the most infrequently found element, they'll say Fred is 10% of the time we look up, turns out over the long run it will have turned out that Fred gets looked up 10% of the time. Well, if Fred is now sitting at the end of the list because of that, because we don't look up Fred too often, so Fred's sort of sitting there near the end of the list, as soon as we happen to make one of those rare lookups on Fred, Fred's right away at the front of the list. And until Fred, everything else jumps in front of Fred and Fred ends up at the bottom of the list again, Fred's going to be interfering with all the other lookups. Where for transpose, since our adjustments are small, refinement is easier, which means we can get very close to optimal. Whatever the optimal list would have been in hindsight, transpose will just about get there. And then any lookup we do only changes the list a very little bit from what it was before. So since each lookup doesn't make drastic changes, we'll be able to get very, very close to optimal, because we're only fine-tuning the list with every lookup. Where here, we're taking something and pulling it way to the front, even if it had been at the end. And so it's hard to use the move to front heuristic to get the list too refined. It gets from, however, disorganized it was, to pretty close to optimal very quickly, but then doesn't tend to do much better than that. Where the transpose will take longer to get close to optimal, as this does, but then we'll be able to refine even past that because we're not making these big adjustments. It's like if you're trying to drive and you drive a car and you keep swinging your hands to the right and swinging your hands to the left, very radically, your car is going to be weaving all over the road because the changes you're making are so big that you're not able to really refine your movement. Where typically how people drive is they make small changes to the steering wheel, just a little bit. And so, you sort of refine your path. You start to drift off straight. Small refinements keep you on a straight list, as opposed to these drastic, weaves if you're violently turning the steering wheel. I probably should have done it like this instead to make it easier for the camera. And it's the same principle here. So these two are sort of counteracting ideas where any time if the list starts out bad, or if suddenly the amount of time it's taking to do lookups is changed. So if we say, oh, it seems like, we've had a pretty settled list, and then suddenly I notice, in the last 100 lookups I've done, I've been looking up always nodes in the very end of the list. So perhaps my percentages have changed. Maybe it's a new semester now, and Sue has dropped some clubs, and Fred has joined some clubs, and suddenly we're looking up Fred a lot more. Well, we can have some measures, like maybe we keep track of, how deep the average node is that we've been looking up over the last 100 lookups or something like that. And we say, well, I note it seems like I'm looking up more expensive nodes lately. The situations may have changed. Maybe whatever probabilities these have been up to this point now have changed. The dynamic situations changed. And it's to say that would be the case with these clubs, where if a new semester started, we'd certainly expect, however frequently we've been looking up Sue up to this point, if Sue drops some clubs and Fred signs up for some clubs, we'd think, well, now starting counting now to the end of this next semester, Sue might be looked up a little less than before, and Fred might be looked up a little more than before. And of course, the structure doesn't know who is important and who isn't, but the structure could notice that, you've been doing a lot of lookups of infrequent, further down the list elements lately. Maybe it'd be a good idea to convert from transpose to move to front. And let move to front work for a while, and sort of, if your projected probabilities have changed, move to front would be dealing with such a thing by saying, well, I'm assuming that the list is bad now, because given the number of lookups deep in the list you've been doing, probably your situation has changed in real life, and however this list is set up now, it's not really well set up for whatever probabilities you're currently experiencing in life. So I'll convert to move to front, and I'll start doing some very strong adjustments. And after things have settled for a bit, then I can convert back to transpose and refine things a bit. And if I notice again that, oh, gee, the last 100 lookups, I've done a lot of searchings deep into the list, I can convert back to move to front. So these two are sort of complementary in that sense, where I can say move to front will allow me to make very quick adjustments, and then I can switch to transpose to refine those adjustments. But then if I need to, if suddenly my existing list isn't really set up for a new situation that my probabilities have changed in a way, or the elements now for whatever reason are being looked up in different frequencies than they were before, and if we can detect that, hey, something seems to be amiss here, then we could switch back to move to front. And so what you really want to get out of this lecture, besides the discussion of the set ADT, all the expected value stuff and that, don't even worry about it. The point is this slide here is the important one. The two heuristics, move to front and transpose, and what the benefits and drawbacks are to each of them when running them on unordered lists. Because each of these will take an unordered list and presumably refine it given our most current information, so that what we're trying to do is keep this unordered list as close to optimal as possible. It turns out move to front is guaranteed to give you a list where your expected number of lookups will be no worse than twice optimal. You don't need to remember that for the exam, but I thought I'd let you know, and it's in the book too. This is going to guarantee the number of expected value of lookups here will be no worse than twice what the optimal one would be. So if you had a 500 cell list and you only expected to have to look at 100 nodes in the optimal situation, this would be double that, 200, which is still better than some nasty arrangement that would give you 450 out of 500. Transpose turns out to be even better than that, but like I said, it just takes longer to get there. And that's about it. That is the end of that topic. And next time we'll be dealing with skip lists. So I will see you then.